Okay, so let's get started. Right, this has been, again, it's been a while, but um, I've been traveling, so couldn't help it for work. Now that I'm actually back, I could get started with, the what we were covering in the previous stream. We talked about, where's that? Oh, wait, I am here. So we talked about this interesting project called CubeCL. Let me see if this is yeah. Um, so this particular project effectively sort of looked at it. It's a multi-platform, high-performance compute language extension for Rust. Uh, we'll break that down, but basically, you can write GPU code, or rather, programs that run on your GPU could effectively be written in Rust rather than the existing options that we have. I'll talk about the existing options. Um, so we basically looked at this, and it's a very interesting project, or rather more intriguing. So I thought, as I said, I'll be looking into this a lot more. There's part one of this, which covers this in some, we get an overview of this. But in this session, because I had some time over, yesterday, a couple of hours to look at this and figure out what's going on under the hood. So we look at the CubeCL architecture, at least things that I understand, and then we look at basically how do does this thing work? So no points over there, but I think we're basically converting Rust to an existing shader language. So shader languages are what you typically use to write code for GPUs. You have many different kinds of shader languages. The one that we'll be talking about today is WebGPU's shading language called WGSL or WGSL. Likewise, there's, let me actually make a note here. There's, sorry, there are shading, sorry, there are shading languages that, if you just were covering them, you've got WGSL, which is the web GPU shading language. I'm not going to, okay, let me just write. Okay, I changed my keyboard, so that's gonna keep happening. And then you've got stuff like, I don't know, the GLSL. So this is from the OpenGL folks, I think. And then you've got HLSL. This is a high level, it's also called high level shading language, I believe. And then you've, I think you've got a few more. Well, yeah, you've also got the metal shading language, this is from Apple. Uh, Pretty much their language or the language that you use to talk to their GPUs. So you've got a bunch of them, all right? The key thing about shading languages is specifically these languages are domain specific in the sense they're purpose built to uh, write code for the GPU and take advantage of the massive amount of parallelism that a GPU offers. So there's a lot of constructs in these languages that specifically cater to the whole idea of maximizing parallelism in many different ways. Well, we're not going to touch that on that subject, at least now. What do these languages look like, etc. But I think you'll get a feel for it if you just look at CubeCL, because it's pretty much trying to take Rust. So we're pretty much trying to take Rust and convert it to this language, any one of these languages, uh, because technically when we convert something to the web GPU shading language, web GPU itself is built on top of the native GPU APIs. In Mac or in the Apple world, that's Metal. In the Windows world, that's DirectX. And then in the Linux world, that's Vulkan. So all of them pretty much use one of these shading languages, and you write your code in Rust, the job of CubeCL is to actually translate that to WGSL. But then again, when you use WebGPU, you know, the underlying implementation of WebGPU, that converts it to, any one of these other languages, like, for example, NSL. So we're not going to cover this part, the second part. So we're just looking at what CubeCL does, which is this part. And the advantage over here is, as you know, being able to write something in Rust. I think they've explained it well on their website. Why would you want to do this? Because the goal of CubeCL is to ease the pain of writing highly optimized compute kernels that are portable. So portability is one of the biggest things that you want, and it's very difficult to do that because today you know, you have some established players like you've got CUDA, and then you've got ROCm that AMD provides. Now, CUDA and ROCm are not specifically, they don't fall into the shading language category. I would just call them the single source category, for example. So this is one way of programming the GPUs. You can also have, let's say, let me try this. Oh, single source, you know, single source method. Okay. In this, you got CUDA, you got ROCm, I think this is how it's spelled, ROCm, and then OpenCL. I believe you also have HIP and SYCL, but they're just built on top of OpenCL. So pretty much, so the biggest difference between these two methods is you write your GPU code, which is also called shader code in one of these languages, and then you write your host code that runs on the CPU in a different file. So you've got two different files. Then your host code pretty much does the compilation of your shader code and then launches that with the required number of threads. So there's a lot of the API is a little different when you work with shading languages. It's not a little different, it's widely different. Whereas with the single source method like CUDA, everything is written in a single source file. The CPU code and the GPU code is in a single file. The GPU code is usually referred to as the kernel in CUDA, etc. And then you basically, go ahead and compile it all at once using, let's say, NVIDIA's compiler or AMD's compiler or whatever OpenCL implementation we have. There's a bunch of different ones of them. You can use that. Here, I would simply put all of this stuff like SYCL and one API and I don't know, maybe HIP. So I'm not completely sure exactly where the lines blur and what is different, etc. But I would just bucket all of them into one space. So those are the two different ways to write code for the GPU. We are going to be looking at this particular part, which is how does CubeCL take Rust code and simply translate that over to, a shading language. In our case, WebGPU's shading language, which is called WGSL. So I've already looked at this, so I don't have to like sit and make this stream like, I don't know, 6 hours long. So just to keep it short, I'm going to cover the CubeCL architecture. So there's actually the way um, the way CubeCL is architected is that I think there's three different constructs. I'm not sure if I'd want to call them abstractions, but I'll just call them constructs right now. There's something called a compute client. Then there's a compute server and a channel. I'll sort of show you what I've understood, the way they've implemented it. And the fact that if you actually go and look at the implementation, so let's actually jump to the implementation rather than turn around. So you've got crates. So this is the kubecl implementation, all of it. You've got a bunch of different crates in here. kubecl core is the main one that has a lot of the core components baked into it. The core constructs are baked into kubecl core. And then you also have kubecl runtime. And then for each of the different backends, like the ones I mentioned here, if you are trying to translate, by the way, kubecl does not just do Rust to WGSL, but it also does, my keyboard is really horrible. kubecl also does Rust to CUDA. All right. So they also have, as you can see, a CUDA backend. All right. Just so that you know. But we're only going to cover WebGPU because I'm running this stuff on a Mac, and CUDA is CUDA is NVIDIA proprietary. So you have to have an NVIDIA graphics card in order to work with it. I don't have one. But the everything that I'm going to discuss pretty much applies to both, right? So CubeCL provides two runtimes. This is runtime CUDA and runtime WebGPU, all right? So let's actually look at what happens in the first step, because the easiest way to understand something like this is to go ahead and look at the example, which is good. So you can actually go step by step and figure out what's going on if you have no idea where to start. So here you go. So if you go and look at the source code, this is pretty much the part of the example. There's an example called GELU, which is, I believe this is the Gaussian uh, error linear unit, whatever, something, right? So if you like, let's just look it up. I forget when I keep saying this. This is an activation function as far as we're concerned. When we talk about machine learning, there are things like activation functions, which I'm not going to cover at this point. I'll just talk about GELU full form and machine learning. Yeah, it's a Gaussian error linear unit activation. Okay, just know that. All right, it's easier to understand in that way. It's basically some function. We don't care about what it does. We just want to know that. We just want to know how this is basically what you would write in Rust that gets translated into Wixel, but you want to know what's being written. So that's the reason I just talked about at least in name. Some of you may already know this, so if you're watching this. But when you look at it, this is the implementation. Now you're not going to be able to make heads or tails of it, but this is what CubeCL refers to as CubeCL kernels. So if you take a CubeCL function and then annotate it with, these two proc macros, either one of these others, you have a CubeCL kernel, right? Effectively, that function can be mapped to an equivalent WebGPU shader code, all right? So that's effectively what we're looking at. But how does one get started? If you go into your uh, example, you'll see that there's actually a main function. And then in this case, I specifically hard-coded it. I've actually modified a couple of things. So I've set the feature to WGPU so that, I don't have to deal with a whole bunch of debug launch files, etc. We'll just start with this. So effectively, we're using the WGPU runtime that's provided by CubeCL, and then we would like to launch a CubeCL kernel, right? So let's look at what happens over here. So if I just, jump into that particular function, that particular launch, you can say that particular launch, you'll end up over here. So the runtime is generic, the device is part of the runtime, etc. All this stuff is great. As I said, the first thing that we need to keep in mind is, we look at the runtimes, they're provided by CubeCL, so you have that. And then we need to figure out these constructs, the compute client and the compute server and the channel. So in simple terms, what the compute client is, I've done this stream a while back, wherein you actually work with the WebGPU crate in Rust that lets you use the WebGPU implementation. So effectively, CubeCL does make use of the WebGPU crate because that's how you can provide a WebGPU abstraction. So the first thing is for you to go ahead and create a compute client. And the way you do that is, you basically go through all of these hoops, all right? Because this is a generic implementation, you wouldn't know how to get started. But the easiest way to do that is, go to the runtime. And if you look at the runtime, you will see a whole bunch of stuff. By the way, this particular project right now is under construction. So there's a lot of things that are probably changing, and I see them changing every couple of hours actually. One thing I do see is there's a serious amount of abstraction, which I'm not too sure I'm in favor of, but it is there at this point. Let's see how this turns out. But there's levels of indirection in there. There's multiple levels. Anyway, coming back, we've got a WebGPU runtime. And what do we need to know? If you go back and look at, what's that? We go back and look at our function, you say that runtime must have an associated method called client. Great. Let's find that. So yeah, so the runtime method or the runtime trait effectively provides, sorry, the, the runtime trait effectively provides one method, or rather a couple of methods, of which you will need to implement the client method. So if we go ahead and look at that, you will see that, oh, okay. So without getting into a whole lot of detail, there's also another crate called pollster being used, which should tell you that there's async await. There's probably multiple threads that are going to be involved over here. And you can already tell we've got mutexes. So you don't like you need to jump into every little bit, but just know that there's a runtime, and that runtime basically has you'll have a method called client that it implements. The job is to return a compute client. A compute client essentially wraps the most important, uh, you can say, concepts of WebGPU. At least when we're talking specifically about the WebGPU runtime, things like the adapter, the device, the queue. So, I mean, just in case you get lost in this point, I did manage to put together something. So if you go to the Mozilla documentation, you'll be able to clearly figure out what these constructs are. This has nothing to do with CubeCL. This is just part of the WebGPU spec. So you usually have a GPU, then you'll have a driver, all right? The driver is usually provided by the GPU vendor themselves, or it could be open source, depending on what you're thinking about. But anyway, and then you could layer that because it's really hard to work with the driver directly. You layer that with a native GPU. This is Metal or DirectX or Vulkan or whatever. And then on top of that, you could also have what you call a web GPU. That's not shown over here. You could have a web GPU layer. This is the web GPU layer. That web GPU layer will have its own abstractions. So the web GPU sits on top of the native GPU APIs, and the adapter is basically the bridge between the native and your web GPU implementation. So each app can get its own device and then start working with it. So you have like a single adapter for your multiple concurrent applications that could be running, and they're all using the same driver underneath, right? That sort of makes this a very, a modular, well-structured, organized stack, or whatever you want to call it. But basically, that's it. So you get that, and then you go ahead and create your client. But the thing about CubeCL is that the client is basically a wrapper. So the client is basically a wrapper for a channel and a server. And in other words, if you actually went ahead and looked at the client, you'd see that once you get your WebGPU specific data structures, like your adapter, your device, and your queue, you can go ahead and create your client. The other thing that you should also know is, there is what we'd call a memory management strategy that you would need to allocate and deallocate stuff, which I will not be getting into because that comes later. We'll talk about it later maybe. But essentially, there's a memory management strategy that's being adopted for how you allocate memory for the GPU to use it, like so that you have buffers that are accessible by the GPU, etc. All that we'll discuss. And then you create an abstraction or a construct called a structure called WebGPU server, and you pretty much use those two, the channel and the WebGPU server, and you wrap them up in a client, and then you hand the client off to whoever wants to use the CubeCL API, right? So that's kind of what you see over here. The compute client is basically a channel, and some server properties and stuff like that. But effectively, that's what you get. So you can think of it as the way I understood, or I am mentally, throwing up a picture is you have a client, you've got a channel, and then you've got the server. I guess that's what was going through their head. So as I said, again, if you read this, from my understanding, the current implementation includes these constructs, where the channel specifically serves as the abstraction for sending requests from the client to a server. So as we've seen, you set up the client using the necessary, WebGPU data structures, and then you finally end up instantiating the client using the WebGPU data structures as well as the memory management strategy that I talked about. Now, once we have created a compute client, that's when we can perform tasks like, creating resources, things like GPU buffers, executing GPU kernels, etc. We can do all of that using the CubeCL, you know, the CubeCL project. The key thing is when we invoke anything on a compute client, which is basically a CubeCL client, you will end up routing those, uh, methods or whatever you need to the compute server. That's why you have the channel, the compute client, and the compute server, I guess. Um, because the compute server is the one that actually holds the WebGPU data structures. So if you want to do something with the WebGPU API, you go through the compute server. But in order for you, like you just don't use the compute server directly. You go through the compute client, which effectively uses the channel. And then there's the channel is mutex lot and arc and whatever. It's basically concurrent safe. Concurrent, you know, you could have multiple clients that could end up accessing, these resources in a very safe manner. So that's sort of, what you would see. For example, when you come in here and look at the client, where's that? Yeah, you see the WebGPU runtime. I'll come to the compiler bit. It has its own associated server, and it has a compute channel. In the device, we've already talked about it. But yeah, that's a very high level view. I mean, if you jump into the source code, you should be able to figure out the remaining pieces. But here's the structure. That's what they've got going. So that's how they set themselves up first. And then finally, you get a compute client. Now, if you go back here, where is that? When we actually call launch and we call client, that's what we get back. We get a compute client back. And we create an input, and then there's an output handle and an input handle that we have to generate from the client. This is basically resources that are being set aside. Uh, let's say, in other words, this is now a GPU accessible buffer. The output is empty because we will populate that when we have a result that is computed on the GPU. That's pretty much what's happening. Now, the interesting thing that happens is you basically go ahead and call GELU array launch unchecked. And you don't see that function anywhere over here. Like when you try and jump into it, you don't see it anywhere. So I think we discussed this in the last stream where I simply went ahead and what you can do is if you've got all your plugins installed, etc., just expand the create macros. It should give you, the uh, expanded kernels, Rust kernels, that is. You copy that and you simply go ahead and just put it in here. You'll get a whole bunch of errors, which you have to now go and solve. Where is that? So the first one is this. These are relatively simple because you're writing macros. Macros are, you don't inherently expose the internals of a macro to the user, which is why you get to use unstable features. So, but since you want to learn about them, you might just want to go ahead and do all of this so that everything compiles as expected. And now, just to get rid of the warnings, right? So that should just take care of everything so that, when we do compile, we don't see a lot of crap popping up. Again, don't ever do this, just when you're writing production code. This is just to learn stuff and get things moving. So you see that your initial Rust kernel has now turned into something like this. And then you've got a module that's created, and then there's an expand function. I don't know if I can cover expansion today itself, but we'll get to that. And then the most important thing is you'll start to see that we actually created a rep, and we actually start representing the original Rust code, the kernel function, with this struct called GELU array. It takes the same name. GELU array is here, and this is also GELU array. All right. Okay. So that's the first thing that happens here. Now, if you just scroll down to the bottom, you'd see the same launch function again. This doesn't change because there's no macro for this. You'd see that now if I just do a launch unchecked, I can see that, this is expanded. All right, which is great. Uh, Now, I think just to keep this small, I'll cover to the point where we do launch unchecked, because that itself is going to have multiple levels of indirection. So let's get to that part. Now we've covered the basic high-level architecture. I'll just call it what it is. High-level CubeCL architecture. All right, so that's a good way to say this. Now let's actually look at, how are you actually translating this, which is your Rust kernels into native kernels. So if you see this, let me actually get this through. Just a minute. Oh, yeah. All right. So if you see this, what's happening here is we are basically going to go ahead and so you might see a lot of underscores. That's just the way people write macros now, I guess. That's about it. Um, yeah, don't worry. I mean, it's the underscores don't mean too much. It's just a convention that's being followed at this point. Anyway, so when we do our launch unchecked, we pass in the client, which we just acquired, and then cube count is basically I'll explain that. Wait, and then you've got cube dimensions. So yeah, let me actually explain those two first because those two parameters are quite interesting. You can go in over here and actually look at the topology equivalence. So cube count technically doesn't have an equivalent for with CUDA and WebGPU, but when you talk about cube dimensions, that also doesn't have it. But effectively, what we're saying is we're talking about think about it in the form of in CUDA or in other GPU frameworks. Think about your grid, then your block of grid of blocks, and then your thread blocks. In each block, there's a collection of threads, and then within that, you can also have things like warps, all of that stuff. These are equivalent terminologies used by CubeCL, right? So they just have their own terminology because I guess we'll figure that out as you go into their implementation because they're trying to abstract over uh, many different they're trying to provide a common intermediate representation for many different shading languages. So they're probably trying to use their own terminology so as to not conflict with in different scenarios. Anyway, and then the important thing is the input and the output. So because we've already changed the example here by expanding the macro, if you want to look at the example again, we will, by the way, this stuff needs to be updated. They've changed it. So if we go into the examples and just look at the example here, you will see that uh, yeah, you will see that the launch function, you are basically actually taking here, the input is an array, the output is also an array, as you probably saw from the initial setup. This is an actual array, and then the output also needs to be an array. So we create these two handles, and then we pass them into what is called this arg array struct, which is basically a CubeCL implementation. It's a CubeCL abstraction for a handle to an array. And also, if you want to add some vectorization factor, which is interesting. We're not covering that, at least not right now. We'll get to that. And then you're able to create an arg array from that, from those two. And that's kind of what you're going to be passing in to this launch unchecked piece. So what does this launch unchecked piece do? Let's take a look at the flow because I just written that down. The first thing that you should notice is for every single CubeCL function, you don't just arbitrarily use standard Rust types. CubeCL functions only accept CubeCL types. That means effectively types that implement the CubeCL trait. And it's not that difficult to look at it, but if you were to, for example, look at this, where is my CubeCL type? Right. So let me figure this out. Just give me a minute. Where did I put my CubeCL trait? Yeah, this project is pretty big. So yeah, it should be in core. So CubeCL trait, where did that go? Where did that go? Where did that go? Yeah. So if you go ahead and look at this, you will see that our arrays implement the cube type. That's the most important thing. So, sorry, you should have an implementation for cube type, and there's no specific implementation for it. It's just that, it needs to implement that so that CubeCL can mark this type as a CubeCL type, right? So those are the only ones that can actually be used inside a CubeCL function. That's the first thing. The second thing we already know right now is we've seen this CubeCL kernels are basically procedural macros. You annotate, if you've annotated any function with this particular macro, then you have a CubeCL kernel, right? The thing is, this stuff actually expands out into uh, a particular proc macro expansion. Now that proc macro expansion itself is used to generate a CubeCL intermediate representation. That's the key thing. That's the key point. You are not taking a proc macro and directly generating an intermediate representation that will be translated to, the shading language. It's actually, you first go from the proc macro to an actual Rust function, which is the usual thing you do, and then you go from there to your CubeCL intermediate representation. The reason they do that, I guess they'll explain that in a couple of places, but if you look at the README, let me find the README. If you look at their README, they talk about, why they're doing that. They get, you basically get comp time and automatic vectorization and a lot of this stuff, right? So you get some cool pieces. But my thing is, this is only useful. The biggest use case for this is you can do a lot more optimization early on at comp time. So that's really useful. Automatic vectorization, there's always hits and misses because there's different things that you have to look at when you talk about vectorization. We'll get to that part, but yeah, that's part of why we're doing this. So anyway, so that's the second thing. So one is all CubeCL functions take in CubeCL types, and CubeCL kernels basically expand, the proc macros expand to Rust functions, and Rust functions themselves will produce uh, the intermediate representation when they're invoked. That's the key point. Now let's get back to the next flow, just to keep things short. If I was to look at the launch unchecked function, I see that, well, there's a couple of things that happen over here. So as we said, in the above example, the CubeCL function annotated with this particular macro expands into a module containing the GELU array struct. We've seen that. We've seen that here. Where is that? Yeah. We've seen that here inside of the GELU array module. We see the GELU array struct. And then I just put it over here so that it's simpler. So what does it contain? It's actually wraps some kernel settings and some, some type information. This is usually not available when you compile it, but it has some type information and some kernel settings. So the job is these kernel settings basically allow us to configure various parameters, things like vectorization factor for the inputs and the outputs provided. I haven't discussed what vectorization is for people who may not know what we're talking about. I'll get to that part. But just know that, the best way I can explain that is, I've actually mentioned this here. So let's say you've got a vector or an array of a bunch of floats, okay? So when you say a vectorization factor of 4, it basically represents a 4-element vector of floating points. You could process that in a SIMD manner. That's what a vectorization factor is. So we basically need to instantiate the GELU struct, and that means we need to have a kernel settings struct for that. And then we also need to instantiate the actual kernel launcher that's going to launch our kernel. So that's kind of what we would see in this case. So that's what happens here first. You go ahead, you see that, you create a kernel settings, default dimensions and all of that stuff. And then you configure the input. This basically sets things like vectorization for input and output and all of that stuff. And then you create a new GELU array. This is basically your kernel, right? The next step is you create or you instantiate a kernel launcher. Now, a kernel launcher might look something that's, oh, interesting. You're launching a kernel right away. Not really. It's got a bunch of things that it holds on to, but effectively it's trying to prepare a kernel for launch. You Rather than me sort of explain that in words, we'll see what that means, because these abstractions tend to be, as the name says, they can get, there's quite a few of them, so you can get lost. That's what I'm trying to say. Anyway, so the inputs that you've received, you register that with the launcher. You also register the output with the launcher, and then you simply go ahead and launch. What does registration actually mean? It means that, so you've already seen the launcher. The launcher has, in this case, if we think of the arrays as tensors, the launcher wants to keep a track of what the inputs and outputs are. So it's basically the array state or the tensor state is that's going to be tracked. So you can either have, it can either be empty or it can either be something. So you're basically going to track that information in this particular struct. So great. And then when you launch, when you actually do a launch, as I mentioned previously, if you've seen, you remember, I mentioned that the key point is invoking methods in the client will eventually route them to the compute server, which holds the necessary WGPU structures to access these resources. Because when you're going to launch this stuff, right, you're basically going to do the translation, and then the translated WGSL kernel is going to be passed on to the entire runtime, and the WebGPU runtime takes over, and then you further compile that for your particular platform. In my case, that's going to be for the Metal API, and then you go forward. So all of that needs to happen. So if you look at this, if you actually just follow the calls, this is all static analysis. You don't even need to set breakpoints and do dynamic analysis or any of this. And that's the key. That's the other thing about Rust. You can, because it's strongly typed, you can just follow the types through, and you'd be able to get most of the way, usually. But then you'd run into some really weird abstractions, and then you'd be like, okay, wait, let me debug this a dynamic way. But in any case, so what happens here? You have bindings. Bindings are, we'll get to this, but bindings over here, keep in mind there's something called a bind groups construct in WebGPU. Effectively, again, you're trying to group resources together, and then you're trying to bind them uh, to the shader code uh, that wants to use them. So there's a way to do that. You'll have a group of resources that are laid out in a certain fashion. Then you have a bind group layout. Then you have a bind group itself saying, okay, these are the resources inside that particular layout. Lots of things. All right. But in any case, and then you basically box that kernel that we just put together. Uh, and then this is the main part. This is the compiler that will do the translation from your existing, format that you've got to the WGSL format, right? That's what they're saying. The compiler used to compile the inner representation into tokens. And then you basically go ahead and, again, so if you notice this is the kernel launcher's launch method that you call it. This calls the client's execute method. This is what we mean by executing kernels. But if you go ahead and execute it, you'll end up here. And this is basically a trait. This is a trait reference. This is a method within a particular trait called the compute channel trait. If you track this down, you will track this down in WebGPU. You will see that because let's just follow this. You'll get to the part. Where is that? So I have the compute server, and if I just go to the top, also before that, before you get lost and stuff, this is the runtime, you remember? And the server over here is what? The WebGPU server. So the WebGPU server's implementation is right here. As you can see, it contains all of the different, it's holding pretty much all of the important data structures that you need in WebGPU. And if you go ahead and search for execute, which is somewhere here, yeah, this is execute, right? This is what executes the kernel over the given memory handle. If you go ahead and see that, so the client actually routes that call onto the server. That's what we mean by having a client, the channel, and the server, right? So I hope that started making sense. So you get here, and then you look at the pipeline, you will see that there's a function called compile. All right, now this is going to get long if I continue with this. So I will not do that. I'll break this into two pieces. So we'll get to the kernel expansion part next. But basically, that's what's happening over here. And that's kind of what I've captured here. So the kernel, the GELU array struct is something that implements the kernel trait. So that's what does the entire expansion of the kernel, and then you get an intermediate representation. That intermediate representation is further translated into the underlying shading language for your platform. Yeah, so that's sort of what I wanted to cover, at least for now, because if I do jump in there with all these macro expansions, it's very easy to get lost. The last part I'll just say is, you've got the GELU struct, and then you also have the kernel implementation from GELU. This is where you actually do this. This is exactly what I meant by your Rust kernel gets expanded into a Rust function, and then it produces this code, which is effectively going to help you create an intermediate representation. That intermediate representation is going to have a one-to-one mapping between, WGSL and that intermediate representation. Okay, just for your benefit, so that I leave you with some interesting pieces. Let's see what that looks like. So I've actually got that stuff here. If you were to look at WGSL, and so, right. So what you have here on the left-hand side is what's going to be generated for that GELU example. This is the actual WebGPU shading language code. And this, what you see over here, is the intermediate representation for CubeCL. If you look closely, you'll be able to see the same thing. For example, let's just take the first statement. It says, this is a variable. It's a storage buffer. It has read-write permissions. Its name is input0 global. Type is an array of float 32. Let's look at this. So this is the inputs. The binding, again, the location is in storage. The visibility is read. Sorry, so we should be looking at, yeah, the visibility is read. And then you also have, what is that? The item is float 32, which is this particular part. Vectorization stuff is only part of the IR. And then you can also see the same thing over here as well for this particular, the second one. And then if you want to see even more information, you can start seeing things like info. This is a named variable that you'd want to use. So we'll get to that part. So basically, you're trying to map this IR straight over to this. And these constructs like grouping and binding, all of it, this is what I meant by bind groups. So these three resources are part of group 0, bind group 0. And this is binding 0 within that group. This is binding 1. This is binding 2 within that group. All right. So both of them, in this case, both of them are just, all three of them are arrays of, one is an array of float 32, one is an array of U32s, but you could have other kinds of buffers in there. All right. So we'll look at that later. But effectively, this is what we're attempting to do. Convert this into this. What we've seen so far is the high-level CubeCL architecture. And then we've basically seen, how you get to the part, how this macro expansion takes place, and how you get to the good part of, launching the kernel. That's what we've seen. The next step, we'll see preparing the kernel, where we talk about, the whole concept of variables and operations and how the expansion takes place and a whole bunch of things. So we can look at those things next. Yeah, so without spending more time on this, that's about it for this particular stream. Thank you.